In this video, we will show you how to use CESAR 2D for the modeling of an anchored diaphragm wall. Diaphragm wall is a retaining technique used in works for deep excavations, especially in urban areas. The objectives of using a FEA model are numerous. Among them is the accurate modeling of the soil structure interactions by using an appropriate soil constitutive model and the design of the structure by calculating the design efforts in the structural elements. The FEA model will also allow to represent the work sequences by editing the several excavations, the variations of the water table level, and the setup of the diaphragm wall in the anchor's layers. First, we explain how to use 2D instead of 3D. The real project to be designed can show preferred dimensions. As illustrated, this excavation is like a box with anchor's layers. It is obviously 3D. We can make the hypothesis that a plane section represents the behavior on the width. Thus, we can model this cut under plane strains conditions. More, we point that there is an horizontal symmetry. Therefore, the model that we will study is reduced to this geometry. We will therefore show how to edit geometry, create the mesh adapted for the calculation, affect properties of the HSM constitutive model, activate the anchors with pre-stressing, edit the different calculation stages, model the movement of the water table, and finally, after the calculation, analyze the essential results. We start by editing the geometry. We set a grid of 5 meters for an easy input of the points and lines. Using the points tool, we create the points and the lines joining them. We follow here the sketch proposed in the support document tutorial 2g.01 on 3w.cesarlcpc.com. The wall is modeled by a 1D body. We simply select the support edges and use the tool for the 1D body construction. User can also assign a relevant name. Now that we have edited the lines and the points, we insert the anchors. They are composed of a free part, not connected to the soil. This is modeled with a node-to-node 1D body and completed with an anchored part connected to the soil. This is modeled with an anchored 1D body. Edit the angle and the length of each part and select the location where they are attached. As the two rows are similar, we generate the second row of anchors by simple copy of the first one using the translation tool. We complete the model by editing the interfaces on the wall. We distinguish the upper part in soil 1 and the lower part in soil 2. Open the tool for interface bodies construction. Select the edges. Give an appropriate name and apply. We edit here the colors of the various bodies. It is optional, but it will ease the recognition as well as the selection of the bodies. Use the vertical color palette for the assignation, left-click, or the selection, right-click on the specific color. The meshing process will consist in generating small elements in areas where high stress gradients are expected. Then a transition towards larger elements on the limits of the model will be applied. We start by fixing divisions of 1 meter on the excavation edges. We continue by applying a division of 10 meters on the outer limits. Now we complete with a transition from 1 meter to 10 meters. Quadratic interpolation is required as we use interfaces and advised for the accurate calculations of plasticity evolution. We need to mesh the 1D bodies in priority as the surface mesh will connect to them. Open the 1D body mesher tool. Set to quadratic interpolation. Select all the 1D bodies and apply. Then we mesh the surfaces. Open the surface mesher tool. Set to quadratic interpolation with a triangle shape. Select all the surface bodies and apply. We can here invert the orientation of the 1D bodies so that the results will have a pertinent sign. As we have completed the geometry and the mesh, it is the good moment to save the file. Let's edit now the several stages of the excavation process. We start with the definition of the effective initial stress field. On the model tree, on the left of the window, right-click on Statics and select Add a model. The toolbox displayed allows to set the name of the stage, to add a comment, to define the plane strain hypothesis, to set that we will generate a staged construction analysis, to set that we will initiate a general initial stress field by the input of the water table level. Validate to close. We proceed now to the addition of the various properties sets, starting with the soil properties. Referring to the support document, we input the values for the sand number 1. Its behavior follows a non-linear elasticity with an hardening plasticity criterion. We assume that the process if fully drained. Use the Create button to generate another properties set for the sand number 2. Adjust the values where necessary. Click Validate to save the data and close. We edit now the properties of the 1D bodies, starting with the wall. It will be loaded in flexion by the soil pressure. Therefore, we define a beam with concrete properties. The section reflects that we are in plane strain conditions. That's why B equals 1 meter in depth perpendicular to our working plane and H equals the real wall thickness. Here, 0.8 meters. We add another set of 1D properties for the definition of the anchors. They will work in traction compression, that's why we select the bar type. We input a module value, a pre-stress force and a section. The section unit must be edited in the unit settings. Here again, the values of section, module and pre-stress reflect the plane strain conditions. Click Validate to save the data and close. The last set of properties to be edited are those of the soil wall interfaces. These joints will be decomposed in 2 sets as there is an interaction with sand number 1 on the upper part and with sand number 2 in the lower part. We will also have 2 behaviors for these interfaces, bonded when the wall is inactive during the initial stress field and friction when the wall is activated. Use the Create button to generate another properties set for the joints. Adjust the values where necessary. When editing the properties of the column's friction behavior, E is a stiffness fixed to avoid numerical issues, RT parameter is the tensile limit. It prevents the opening of the interface if the normal force is inferior to this value. The friction angle is valued at 2/3 of the soil one. Click Validate to save the data and close. We can now assign the various sets to the items of the model. We choose here the method to select with the color palette. Right-click on the toolbar selects the bodies with same color. Select the set in the properties grid and apply. By adjusting the type of selection on the selection toolbar, we continue the affectation of the properties set on the 1D bodies, the anchors, then the wall. Finally, we assign the bonded properties on the interfaces. We can also check that all the bodies of our model have a assigned properties set using this Assign View tool. Let's focus now on the activity of the bodies during this stage dedicated to the analysis of the initial stress field. The anchors as well as the wall are not in place yet. Therefore, their activity is set to inactive. The inactive state is illustrated by the display in gray color, default inactive color. We fix the boundary conditions on the limits of the model. Using the predefined tool, we lock the horizontal displacements on the vertical edges and lock both displacements on the bottom edges. The load in this stage is the definition of the initial water table level. Using the definition tool, we assign the constant level of -3 meters. We must complete the definition of this load by the assignation of the unit and saturated weights to the surface bodies. Thus, it will generate the appropriate effective stress field. To complete this stage definition, we adjust the analysis settings. In particular, the iteration process is modified so that we have 2 increments, as recommended when using non-linear elasticity in the constitutive model. Also, for the tutorial purpose, we will reduce the precision to 1% instead of the default value of 0.1% recommended when calculating highly non-linear models. We check in the Analysis Manager that each step of the model generation is okay. We will launch the calculations later, altogether. Last task for the good identification of our model, we can modify the default names of the boundary condition sets or loading sets. Use F2, edit the name and press enter. We can now prepare the second model. In this model, we will activate the wall and lower the water table level. As a rough hypothesis, we will simplify the setup of the wall and consider it as wished in place. In the calculations tree, right-click on Statics and select Add a Model. In the new toolbox, edit the name of this stage. It is automatically considered as a staged construction process under plane strain conditions. For the easy and quick addition of the properties and boundary conditions, we copy the existing sets by drag and drop. Using the share option instead of the simple copy will automatically update the modifications in one set to those shared with. In Properties step, we define the activity state of the bodies. Compared to the previous stage, the wall is activated, but the rows of anchors remain inactive. Select the anchors bodies. Open the Activity tool, set to inactive and apply. Now that the wall is active, we must assign a friction behavior to the interfaces. Select the upper interface bodies. Select the Set Wall Sand number 1, Friction, and apply. Repeat for the lower part of the wall in sand number 2. The next modification is the water table level, lowering from -3 meters to -5 meters inside the excavation. Open the water table definition tool. Set the initial water head constant at -3 meters. Set the actual water table as variable and input the appropriate coordinates in X and levels in Y, then validate when completed. Again, we complete the definition by assigning the appropriate unit and saturated weights. Note here is alternative method that the drag and drop of this load set from previous stage would have helped for the definition of the water table. The drag and drop method is used to copy the analysis settings from the initial stage. By double-click on the item in the calculation tree, we access the addition of these settings. Here, we initialize the displacements as we don't want to consider the settlements associated with the initial stress field calculation. We can now prepare the third stage of construction. In this model, we will excavate the first 5 meters. In the calculations tree, right-click on Statics and select Add a Model. In the new toolbox, edit the name of this stage and validate. Using the drag and drop, we copy the properties, boundary conditions and analysis settings. In the Properties step, we just have to inactivate the 1D bodies of anchors and the surface body of the first 5 meters of excavation. The boundary conditions have been automatically updated. We generate a new type of load that will release the stresses on the borders of the excavated area. Activate excavation forces. Set the stress release coefficient to 1. In the drop-down list, select the reference stress field and apply. With the Show option, we can check the edges where the excavation forces are applied. We rename here the loading sets. Use F2. Edit the name and enter. By double-click on the Analysis Settings item, we edit them. Untick the Displacement Initialization. Thus, the displacements will now be cumulated from one stage to the other. In the modeling process of the excavation works, we insert now a row of anchors to support the wall. In the Calculations tree, create a new model. By drag and drop, copy the properties, boundary conditions and analysis settings. Set to active state the first row of anchors when the second row and the first excavation remain inactive. This activation of the anchors is sufficient to declare the pre-stress force. No additional load is required. The next stages of construction will model the drawdown to -10 meters and the excavation to this depth. They will repeat the operations detailed for the addition of stage number 2 and stage number 3. This is why we are going to go through these steps more quickly. Add a new model. By drag and drop, copy the properties and boundary conditions of the previous stage. Copy the loading set of the first drawdown. Set to inactive the excavation area and the second row of anchors. Modify the water table levels, initial and actual ones. Add the last model. Copy by drag and drop the properties, boundary conditions and analysis settings of the previous stage. Set to inactive the excavation areas and the second row of anchors. Edit the new excavation load. We open now the Analysis Manager. It shows the status of our 6 stages. The check marker indicates that the properties, the boundary conditions as well as the loading sets are completely defined. We can now run all the calculations. Tick here to select all the models. And validate. The process of the data addition and preparation for the solver is displayed. Then, the calculations start and the iterative process is displayed. The calculations process ends with this message. We can also check in the Analysis Manager that each model was calculated and well terminated with the OK message displayed. Let's show now how we can display some of the main results. We start with the initial effective stress field. In type of results, activate the 2D stresses tensor. Apply. The main stresses are displayed at each node. With results info, we can ask for values at any node. Open the tool. Right-click on a node of the model. The coordinates of the selected node and the values of calculated stresses are updated in the grid. We can check the value of main vertical stress sigma 1. We can also check that the horizontal main stress sigma 2 is linked with sigma 1 by a factor K0. The lateral pressure coefficient depends here from the Poisson's ratio. We can evaluate the evolution of the stress field by toggling from one stage to the other using this drop-down list. In the first excavation stage, we focus on the displacements. First, we display the deformed mesh. In the type of results grid, we untick 2D stresses and select deformed as deformed model. We see the evolution in function of the several increments. The displacement can also be displayed under contour plots type. Activate these contour plots and select total displacement in the list of scalars. And apply. Again, by toggling to the stage anchor level number 1, we can see the evolution of the displacements after the activation of the prestressed anchors. We can now focus on the efforts in the wall and the anchors. In the grid, untick contour plots, then 2D stresses. Activate the 1D body results. Select the normal force N and apply. In order to focus on the wall, we can isolate them. Select the 1D bodies and use the Show Selection Only option on the selection toolbar. We can adjust the display by using the 1D bodies results options. In particular, we can display the maximum and minimum values of efforts. Again, by toggling to the following stages, we can check the evolution of the effort's value. Let's focus now on other type of results displays. Here, with the Display Results tool, we can specify what type of results to be displayed per type of body. As illustration, we show here how to hide the contour plots on the 1D bodies. Now we show how to adjust the display of the contour plots. We can add edges. Activate contour plot settings. Tick contour edges and select the gray color set. We can also set the scale as manual so that we can see the evolution of the displacements in function of the increments. In displacement settings, we first emphasize the displacements by increasing the automatic scale. Then we set a manual scale. This will help to illustrate the evolution of the deformed mesh with increments. We set here that 6 meters at the model scale will represent a displacement of 20 millimeters. Thus, we can open the animation tool, tick all entities, and play the animation. Another improvement of the results display stands in the addition of the legend. Open legend settings. Select a larger font and size. Tick with background. And apply. Again, we can use the Results Info tool to ask for a value on a specific location. For example, we ask here for the displacement at the bottom of the excavation or at the head of the wall. Another alternative to the graphical display of the results on the model are the charts. We can graph scalar on specified cut lines. On the selection toolbar, activate the edges selection. Click on the edges of the model behind the wall. Open the line set definition tool. Edit the name and add. It generates an oriented line. Activate the tool charts for a line set. Select the vertical displacement, UY, as parameter and apply. The chart can now be edited so that the axes, titles or colors fit well. We repeat the operation of the line set addition so that we have now a line set on the wall. We can invert its orientation. We open the Beam Forces chart tool. Here we select the bending moment as parameter and the wall as line set. Apply. We show here that the values can also be exported in an external file so that we can plot them with another software or compare them with other results. Again, we can edit the axis, titles and colors. This concludes the presentation of the tutorial 2g.01. For more information, subscribe to our video channel or visit our website.